This is a video which belongs to the course Graph, Homomorphisms and Universal Algebra. But in fact, today's video is relatively self-contained. So you can watch it even if you have not seen the entire series. Previously, we have mainly worked with directed graphs. But in order to build a general theory, we need to generalize this to general relational structures. In this way, we can also model many more computational problems as homomorphism problems. For example, solving linear equation systems over a finite field, or various propositional satisfiability problems can be modeled as homomorphism problems. Also, the pre-colored homomorphism problem that we have encountered earlier fits into this scope. Even if you are only interested in directed graphs, knowing general relational structures is a necessary thing in order to build a general theory of homomorphism problems.
In the script of the course, we are now entering section 4. Here's the output of what happens if you feed this section into the word cloud. In the survey among the students that we have conducted before the course, almost everybody knew about graphs, but almost nobody heard about relational structures. So we need to fix that. The idea of relational structures is to generalize directed graphs in various ways. Remember, a directed graph is simply a set together with a binary relation on that set. The first generalization is that instead of binary relations, we also want to allow ternary or higher array relations. Why just binary? The second generalization is that we want that our structure might carry several relations at the same time, rather than just one binary relation, as in the case of graphs. Imagine that we want to model graphs that have both blue edges and green edges, or graphs where some of the vertices are colored. All this is possible with relational structures. Finally, we would also allow that instead of relations, there are some operations in our structure. Of course, there's a small notational price that we have to pay. We need the different symbols in order to distinguish the various relations and operations, so we need to define this slowly and carefully once and for all. The readers and listeners who know this can jump in the script or in the video. There will be more substantial material later on. In order to define relational structures, we need the notion of a signature, which is simply a set of relation symbols, typically denoted by a capital Roman letter, or R1, R2, and so on, and a set of function symbols, typically denoted by small Roman letters, or F1, F2, and so on. Each symbol comes with an arity, which is simply a natural number. Our typical name of a signature is a small Greek letter, such as sigma, tau, rho, and so on. A tau structure consists of a set, also called the domain or universe of the structure, and for each relation symbol in tau, a relation of the corresponding arity. And for each function symbol in tau, an operation of the corresponding arity. Note that by using superscripts, I really make a distinction between the symbols and the corresponding relation or operation. Often, authors use the same symbol for the relation symbol and the relation itself. But this is only because they know the correct definition and they are a bit sloppy with using it. The distinction is important, and in particular when it comes to applying formal logic to study structures. We typically use the same letter to denote a structure and its domain, with the only difference that we underline the letter if we mean the structure. In the script, underlining is not so nice, which is why we use fraktur letters instead of underlining. To specify a relational structure, there is the convenient notation to simply write down a structure similarly to graphs as a tuple, whose first entry is the domain, and then comes a list with the relations and the operations. Math students know plenty of structures. For example, the ring of integers with two binary operations, or the ordered additive group of the reals with a binary operation and one binary relation. From a computer science perspective, one may view a structure as a database. Here I have an example. Your database for a course might contain a table where the entries are 4 tuples consisting of a student name, an email address, the major subject of the student, and the number of points, total points obtained. This could be modeled using a 4-array relation. The entries of my table would be the 4 tuples in the relation. All the red stuff that you see in my picture would be the domain elements. The black stuff represents the relation. In the picture on the right, you see another type of data, namely the performance of a student over the various exercises. This we could model using a binary function that maps pairs student, exercise to the number of points obtained by the student in the respective exercise. Again, the red stuff is domain elements, whereas the black stuff represents the binary function. We will comment on this computer science perspective on the stuff that we present here later again. Let A and B be tau structures. A mapping H from the domain of A to the domain of B is called a homomorphism if it preserves all the relations and all the functions. For relations, this is really just the straightforward analog of what we have seen for graph homomorphisms. If you apply H component-wise to a tuple in a relation of A, then the resulting tuple must be in the corresponding relation of B. For functions, this is precisely the notion of homomorphism that you know from groups, rings, fields, and etc. If f is a function of A, then h applied to the function value of f applied at some arguments is the same as first applying h to the arguments and then applying the corresponding function of b. Tau structures where the signature is purely relational are called relational structures, and tau structures where the signature is purely functional are called algebras, in the sense of universal algebra. In this section of the course, we'll be mostly working with relational structures, but algebras will become very important in later sections of the course. We will now define constraint satisfaction problems for relational structures. Let tau be a finite relational signature. One might also consider infinite signatures, but the assumption that tau is finite avoids certain technicalities and simplifies matters. Let B be a tau structure. B will be fixed in the following. CSP of B is defined to be the class of all finite tau structures A that homomorphically map to B. We again imagine this as a computational problem. The input is A, B is fixed, and the computer has to decide whether A is homomorphic to B. Let's look at an example. If we fix the domain to be 0, 1, and we just have a single binary relation which just contains the pair 0, 1, then the corresponding CSP is the class of all finite digraphs that homomorphically map to P1, the path of length 1. So this is just an example that we have seen in previous sections of the course. So let's look at a new example, something that we could not model with digraphs. I pick again a structure with domain 0, 1, but this time there are two ternary relations, one containing all triples that sum up to 0 modulo 2, and one containing all the triples that sum up to 1 modulo 2. This is the problem of testing the satisfiability of a linear equation systems over the two-element field with 3 variables per equation. So this is basically the computational problem that we have called lin-EQ in earlier videos.
Today's topic of the break is what's the real reason of the corona outbreak? What was the mistake? Who's to blame? We will have an educated opinion about this topic from the future.
Die Fachleute warnen vor dem Verzehr nicht hinreichend untersuchten Fleisches, durch dessen Genuss Tierseuchen auf den Menschen übertragen werden können.
There is an important alternative perspective on CSPs using logic. So again, we have a relational signature tau. A primitive positive tau formula is a formula consisting of a conjunction of atomic tau formulas where some of the variables might be existentially quantified and some variables are not quantified. Those are called the free variables. I called them x1 up to xn. An atomic tau formula is a formula which either consists of a relation symbol from tau applied to some of the variables, or an equality of variables, or the bottom symbol, which stands for false. If all of the variables are existentially quantified, then our formula phi is called a primitive positive sentence. If you have a tau structure B, then a tau sentence either evaluates to true or to false on B. It should be clear how to evaluate the sentence. We have to find values for the variables so that all of the conjuncts of our conjunction evaluate to true. So for those of you who know first-order logic, primitive positive formulas are like first-order formulas, but negation, disjunction, and universal quantification are forbidden. These formulas are the most important formulas in database theory, where they have a special name. They are called conjunctive queries. In practice, most queries to databases are conjunctive queries. Let's look at an example. We choose the signature of digraphs. That is, we just have a single binary relation symbol in the signature. Our primitive positive formula phi has 4 existentially quantified variables and no free variables. So in fact, we even have a primitive positive sentence. It has 5 conjuncts. I will also give an example of a tau structure on 3 elements, namely the structure that just carries the binary not equal relation. In fact, as a graph, this is just a clique with 3 vertices. We might now wonder, does the sentence phi evaluate to true or to false on B? Here is something important. We can not only view the tau structure B as a digraph, we can also view phi as a digraph. The vertices of this digraph, let's call it A, are the variables of phi. The edges of A come from the disjuncts of phi. In order to evaluate phi on B, we have to find values for the variables so that all the conjuncts are satisfied. Note that this is precisely the question whether there is a homomorphism from A to B. And of course, this is not specific to our example, but holds in general. From every primitive positive tau sentence without equality conjuncts and without bottom, we can produce in this way a tau structure which is called the canonical database of phi, and which has this nice connection between truth and the existence of homomorphisms. Moreover, there is an obvious converse of this connection. To every finite tau structure A, you can produce a primitive positive tau sentence called the canonical query. The variables of this query, or primitive positive sentence, are the elements of A, and you have a conjunct in your formula for each tuple in a relation of A. Because of this correspondence, there is an alternative definition of the constraint satisfaction problem for B, which also can be found frequently in the literature. Now the input is no longer a finite tau structure, but the input is a primitive positive sentence. And the question is whether this sentence is true in B. Of course, this is just a cosmetic reformulation of the earlier definition of CSPs with homomorphisms.
We will now present a fundamentally important result that illustrates the usefulness of primitive positive formulas. If you have a structure, we can use formulas to produce new relations over the structure.
Suppose that phi is a tau formula with k free variables and that B is a tau structure. Then phi defines in B the relation of arity K that contains all those K tuples of elements of B that satisfy the formula over B. In the following sense, we replace the free variables by the respective entries of the K tuple and then evaluate the resulting formula over B. If it evaluates to true, then we say that the K tuple satisfies the formula. If phi is a primitive positive formula, then we say that R is primitively positively definable in B. The following lemma explains why primitive positive definability is so important when studying homomorphism problems. It states that if a relation R is primitively positively definable in B, then we can add the relation to the signature of B without increasing the computational complexity of the constraint satisfaction problem. A priori, if you add relations to your structure, then the CSP of the resulting structure can become harder. But the lemma says that it does not become harder if the relation that we added is primitively positively definable. The reason is that the new relation can be eliminated. We will see how this can be done, but before I will illustrate how useful this is at an example. Let's have a look at CSP of C5. So this is the problem to decide whether a finite graph has a homomorphism to the undirected 5 cycle. Don't confuse this with the directed 5 cycle, whose CSP can be solved by path consistency. If you have a look at the polynomial-time algorithms that we have seen so far, you will note that they do not solve CSP of C5. So at the moment, we don't know the computational complexity of CSP C5. To apply our lemma, consider the primitive positive formula phi with two free variables x and y, which states that there exists a path from x to y of length 3. Note that in C5, there is a path from x to y if and only if x and y are distinct vertices. So the relation defined by C5 is nothing but the 5-clique, called a K5. And we already know the computational complexity of CSP of K5. This is the 5-colorability problem, and it is NP-complete. Hence, by the lemma, CSP of C5 is NP-hard, because CSP of K5 can be reduced to CSP of C5 in polynomial time. The proof of the lemma is actually rather easy once you see the idea. This is why I rather illustrate the proof with an example. Suppose we have an input instance of CSP K5, which in our new perspective is simply a primitive positive sentence. Our instance has 3 variables, x1, x2, x3, and 3 conjuncts or constraints. In this example, it is easy to see that it is satisfiable in K5. But we would like to illustrate a general idea how to reduce the question to CSP of C5. What we do is that we replace each of the constraints by its primitive positive definition in C5. So each conjunct gets replaced by 3 new conjuncts. But note that we also have to introduce new variables. We use different new variables each time for each constraint. This is important. The resulting formula can be rewritten into an equivalent formula such that all the existentially quantified variables come at the front. Then K5 satisfies the original formula if and only if C5 satisfies the new formula. So we have reduced CSP of K5 to CSP of C5. Note that the size of the new formula is linear in the size of the original formula, since we have replaced each conjunct by phi, and phi is fixed, so of constant size. Clearly, the new formula can be computed from the old formula in polynomial time. And that's the idea of the proof.
Big addition, I can go.